Okay, so you've got an idea of, maybe you've got an idea from watching this video, and probably more so from watching the book and the other good videos. I really encourage you, especially if any of this doesn't make sense to you, to read the chapter in the book and to watch those other videos. They're really good videos by people who are better than me at presenting that stuff. So how do we use this stuff? Why do I care? Well, I care because in your career, in my career, I've had to hook up loads that are three-phase loads, and I've had to do some calculations and figure out what size circuit something actually needs. The kind of information that we as electricians are going to get, a piece of equipment hits the dock, and you look at its nameplate. Hopefully it's UL listed. But you look at its nameplate and you see that, okay, I've got a 17,800 VA load that would like a three-phase 480 volt circuit. This is what it wants. It wants 480 volts, three-phase, and that's the size of its load. Well, how do I size that circuit? How do I know how to run overcurrent protection? Let's say, for the sake of argument, they tell me that it is a continuous load. There's my alarm for the last video saying you're done. I'm going to set this one too, just because. Bear with me. Start. I'm going to set this one too, just in case, so we don't run out again. I'm hoping this video doesn't go half an hour, but keep doing that and it will, right? Say they tell me it's a continuous load. So what does that mean? That means whenever I size my conductors for it, I'm going to have to go 125%. I'm going to multiply it by 1.25. You guys probably all know that already. If it's a continuous load, my conductors have to be 1.25 times the ampacity of the wire. When it's a continuous load. I want a little bit bigger conductors for that continuous load. Motors, same thing, but for a different reason. I want that for my inrush and other things. And then you're going to learn more about motors that you can actually size your overcurrent protection and your other things higher still on motors when you get to learning about that. But for the size, we're going to size conductors for this exercise. So if I've got that and it's a three-phase 480, I know how to size my wire by current, but I haven't been given current. But I know that I equals P divided by E times the square root of 3. Now some people have memorized what 480 times the square root of 3 is, and I think it's 832 or something like that. I don't do that. You're welcome to if you want to. The guy that taught me years ago when I was taking my signing supervisor's license had us use, I think it's 832. Don't quote me on that. I know where the square root of 3 button is, essentially, on my calculator, so I use that. But I'm going to solve that. Now, the reason I'm using square root of 3 is because the current is going to be divided by those 3 wires. Remember, I'm sending current out on 3 wires to this load. And those 3 wires are carrying 3 phases between them. Between wire A and B, I've got a phase. Between B and C, I've got a phase. And between C and A, I've got another phase. So between those 3 phases, which are 120 degrees out of phase with each other, I can do a little bit of, not derate, but I can do some calculations based on how the current's actually going to flow. Because all of my current for the power isn't flowing in phase with itself. It's happening at different times, breaking that whole cycle up into 3 parts. Some of it cancels itself out. And we figure that out with that vector math, that 120-degree vector math, which when we do the calculations, you're going to just have to take my word for it unless you want to watch some of the higher math videos, square root of 3 is the relationship between those things. So when I divide square root of 3 out of power along with my voltage, it compensates for that. It takes that into consideration, that on my 3 wires, none of those 3 wires is going to be taking the full current at any point. Each one is going to be taking the full current divided by the square root of 3. And that's why we throw that in there. Again, attach that in a 3-phase circuit when you're doing calculations. Attach that square root of 3 to the voltage by its belt loops. And don't let those 2 things come apart, because when you do it this way, it'll always work. Is that the only way you can do it? No. But is this the way that it'll always work? Yes. And I think that's the reason a lot of people teach, instead of using voltage times the square root of 3, memorizing what the different voltages times the square root of 3 are and just using those numbers. If you want to do it that way, you're welcome to do it. So I'm going to take this formula and I'm going to say 17,800 VA divided by 480 times the square root of 3. Remember, that's all under the parentheses, because that's all get divided in there. I'm going to throw this into my calculator right now. And I know you'll all check me because when I make calculator errors, I hear about it, and I appreciate that. I'm not saying anything different. 17800 divided by, and then I'm going to throw these into a parens. 480. I could have just done the 480 times square root of 3 first and then divided that out of 17,800. But I'm going to go with 480 times second square root 3, and then I'm going to end parens twice. The reason I do end parens twice is because that 3 is the first parent open parens, and I close it underneath the radical, the square root sign, and then I throw another end parens in there to make sure all of that's underneath the divide by 17,800. Let's see if it worked. And I get 21.41. 21.41 amps of power flowing down those 3 conductors to my load. Now, can I take that 21.41 and say, well, I got 3 conductors, so I really only have about, seven and change amps in each conductor and size them for 7 amps? No. 21.41 is the current at each conductor. So I've had a couple people try that on me and say, well, I got, I figured it all out, but it's 3-phase, so I only have a third of the current in each phase. No. You've already taken that into consideration with that square root of 3 for those 3 conductors. It would be like saying, I've got a 20 amp bathroom circuit, but I've got a hot and a neutral, so I really only have 10 amps on either one at the same time. Well, no, the current is flowing all the way through. And the same goes for these 3 wires. Through that triangular Y at the end, that's the 3-phase load, you've got current returning. It's just not all returning down one conductor, it's divided up between the other 2 conductors when it returns. I'm going to kill this phone call, apologize about that, and we're going to return to this. So I've got 21.41 amps, and I'm going to say, well, what size conductor do I need for 21.41 amps? Well, wait, I've also got a continuous load. So this is just electrician stuff that you guys probably already know. It's the actual current, that the ampacity of the wire to carry that 21.41 amps. Remember, ampacity means the wire's rating for current. The ampacity is not the size of your circuit breaker. The ampacity is not the amount of current actually flowing. The ampacity is the wire's rating to carry current. I hear a lot of people use the word amperage. And I always try to discourage people from using amperage because to me it doesn't mean anything. What does that mean? Is that the current rating? Is that the actual current flowing? Is that the ampacity of the conductor? Amperage is kind of a mushy word that electricians use that is vague, and so I discourage people from using it. But the ampacity of the wire that we need to figure out is 21.45 times 1.25. Now that's multiplying something by 1.25 is the same as dividing it by 0.8, right? Because they're inverts of each other. 1.25 is 5/4, and 0.8 is 4/5. So that confuses people a lot, the whole 80% and 125%. Well, if I've got a conductor and I need to figure out how much current can flow on that conductor, I use the 80%. Because I can only do 4/5 of the current on that conductor with the 125% rule. However, if I know my current and I'm sizing a wire to it, I say, well, what's that current times 1.25? And then I figure out what wire that'll take. So 21, this gives me 26.8125. Now, off the top of my head, I think even in 90-degree column, number 12 wire is going to max, I think, at 25. Might go to 30. I don't know, I have to check on that. But I'm going to size my conductor for something that will carry 26.8125, which it's 26 and change. 30 amps, essentially. I want to size for 30 amps, and I am going to, now what size overcurrent protection device can I put on that? Well, I'm not sure. It depends on the load. I may be able to put a 3-phase 20 amp breaker on there. I may need a 20, I'd be legal to put, if I went 10 wire, I'd be legal to put a 25 amp or 25 or even a 30 amp breaker on that wire because that breaker's big enough. I'd have to read the codes on the exact piece of equipment I'm dealing with and figure that out. But for sizing the wire, I think I'm going to go with a number 10, unless somebody can tell me, if somebody has a code book open right now and can tell me if the 75-degree Or if all my terminals in this situation, which I didn't talk about, are 90 degrees, if the 90-degree column of number 12 is above 25 amps. 25 amps. I don't think it is. Well, again, off the top of my head. This is one, if I showed up on a job site and somebody had this set up and they had 10 wire on it, I'd approve it. If they had 12 wire on it, we'd have to open up a code book. And that's the same thing I'm doing here because I don't have a code book right now. So that is that formula. So here's what you should take away from that, is that when I've got this magic wheel, I think the mathematicians call this, for our power diagrams, remember that for three-phase, I'm sticking the square root of 3 right there. So same thing, if I've got, let's say I've got a circuit that is drawing 32 amps, and I know that the voltage supplied, it's a three-phase load, and it's got 208 volt three-phase. That's what it's got, and it's a non-neutral load. So what's my power? Maybe is the question. Well, power is going to equal, P equals I times E, right? I times E, well wait, it's three-phase. I'm going to throw the square root of 3 in there. Now my power formulas are the same whether it's a delta or a Y, I don't care which it is. Especially since I'm using line volts and line current. As an electrician, I'm not going to worry about the phase volt and the phase current. Remember, the phase voltage and the phase current is the current and the voltage interior to either the piece of equipment or the transformer. That's the current through the actual coil or current through the actual one leg of the load. It's the voltage at the actual coil or the voltage at the actual one leg of the load or line to neutral, depending on whether it's a Y or a delta. I'm not going to worry about that. As an electrician, I'm worried about the wire. So my line voltage and my line current. So if you want to even put those up there, and voltage at the line times the square root of 3. In that case, it's 32 amps, and I am burning up markers today, 32 amps times 208 volts times the square root of 3. And that should give me my power in VA, right? Because I'm just doing volts times amps. I don't know if it's watts. I don't know if it's reactive power bars, but it is VA. Clear, and I'm just using the line, so it doesn't even matter at this point. We move beyond worrying about reactive and non-reactive, linear and non-linear loads. So 32 times 208 times second square root 3, close the parentheses just in case, and I get 11,528. 11,528 and change VA. It's actually 0.53, so I should probably round that up to 9 if I'm going to do some rounding, since I'm harping on you guys about rounding correctly. 11,529 VA, or if you really want to round it up, which is what you'll see, 11.5 kVA. So that's the size of that load. Now, that's the same calculation we just did, just the other way. So this is really the important thing to remember about three-phase. When I'm doing calculations on power, is dump that square root of 3 in with my E, my voltage, and go from there, and you'll get the right formulas. If you forget about this stuff and you go to size a load, let's go back up to this one, right? My last one. Let's say somebody dropped this load on the dock, and either they didn't tell me or I forgot about the three-phase. So I'm going to size this same 17,800 VA, and I'm going to figure out what size wire I need. I'm also not going to order enough wire, right? Because I'm going to forget about the third chunk of wire. Because that is the one thing with three-phase, is I need to run at least 3 hots for a three-phase load, plus a ground by code. If it's got a neutral load, I also need to run a neutral. That's a different question. Let's go ahead and do this as though it was single phase, though, and see what size wire we need. On that last one, we decided we could use number 10 and be safe, right? I equals P over E, in this case, 17.8 K divided by 480. What's that equal? Clear on, let's see, 17,800, 17800 divided by 480 equals, 37.2 0, 8. Again, I remember that it's a continuous load, so I'm going to multiply that times 1.25, and that equals 46.35. So essentially, I'm looking at a 50 amp circuit now. Is my number 10 wire going to work for a 50 amp circuit? Not even at 90 degrees, right? For my 50 amp, I'm going to need at least number 8 wire. If it's in conduit, if it's in cable, I'm going to need number 6 wire. If I'm for some reason running Romax or SE cable to this guy, I'm going to need number 6. And if you don't know why that is, it's because cables, especially Romax and SE, which defaults to the Romax in many of its code, requires you to size its ampacity by the 60-degree column. So a lot of times you'll find a situation with a 50 amp circuit that's legal with number 8 wire in THHN in a piece of pipe, depending on other circumstances, you know, how many wires you got in and things like that. Whereas cable, you're going to need number 6. Something to keep in mind. And that's 334.80 in the NM code. But anyways, 50 amps, that's a big area. So here I'm the poor guy that was sent this information by email, right? And so I show up on the job site with a whole bunch of number 8 or number 6 wire and pipe, and find out that not only do I have the wrong size wire, I've got too big a wire, I spent too much money on too big a wire, but I didn't buy enough of it. Because, you know, if I show up with too big a wire, I can still use it, right? I'm always allowed to oversize the conductors, if that's what I got on the van or for whatever reason. But if I only bought enough length to do 2 runs, hot, hot, and a neutral, hot, hot, and a ground, I should say here, 480, I'm going to be out of luck there too. I'm going to end up having to buy some more wire anyways. So those are the ramifications of 3-phase. I want to do another thing. Take a look at how much time I have, if I can do it on this video or not. I have 13 minutes left on this. I'm going to break it up, and we're just going to do 3 videos because it's easier. But I want to talk about high leg 3-phase panels that you will find that are labeled high leg or wild leg or crazy leg. People talk about all sorts of different names of them. Essentially what they are is 240 volt deltas. Secondaries, the secondary of the transformer is a 240 volt delta, and we take the wires off of that secondary transformer and run them into a panel, and it causes havoc. So tune in for that video.